So this short video clip is about how to use a power device reference design to accelerate your switch mode power supply design workflow. I'm Colin Warwick. I'm product manager for PathWave Design Power Electronics here at Keysight Technology. Let's get right into it. So let's first set the scene by looking at some trends in switch mode power supplies. Consumers are demanding a lower cost, a smaller size, and a lighter weight, and that means we have to work on the heaviest, largest, and the most expensive components in the switch mode power supply, which is the magnetics, the capacitors, and the heat sinks, which will attach to these transistors. This is a bolt-on heat sink. And you can achieve this actually by going to wide bandgap semiconductors. These are actually silicon carbide. And you can achieve a higher DI/dt, and that will give you a lower cost, a smaller size, and a lighter weight, it turns out. I won't go into the reasons here, but it's well known that you go to high DI/dt, which is the current slew rate in the switch loop, you can get to better performing switch mode power supplies, which is great, but there's a downside. The traditional, what I call the cut and try design methodology, where you do a bit of pre-layout spice and then build a prototype and try it out, doesn't work very well in high DI/dt, and the reason is that the high current slew rate in the switch loop interacts with the parasitic inductance of the PCB traces and gives you voltage spikes, which can destroy the transistors. It also gives you a high radiation. Both the radiation and the conductor EMI depend on DI/dt. This is the formula for a dipole, Hertzian dipole. And you can see that the far field strength is dependent on DI/dt. So you get into EMI failure problems unless you design this carefully. And the solution is to change your design flow, change the workflow. You need to add a field solver to extract the layout parasitics and the far field to EM using an EM-based model. This is great, but most people in power electronics aren't so familiar with using a field solver, and it's kind of tricky to set up. So we've made this easy for you, making it a very jump start by creating what we call a digital twin of the reference design. Let me explain how that works. Now, it's well known you can leverage info from your power device vendor. If you're dealing with a new power transistor, such as these ones here, silicon carbide, it doesn't make any sense to start from a blank piece of paper and try to design a switch mode power supply, because your device vendors already done some of the work for you. They create a reference design PCB. They're trying to be as helpful as possible to get the device designed in for you, because they want to see volume as soon as possible. So they're providing device models from the power device modeler. They'll take IV measurements, CV measurements for not just internal evaluation, but also input to the datasheet plots. And the application engineer at your power device vendor will give you datasheet sample devices, the reference design PCB, which is already pretty close to what you want to build. It needs a few changes, but it's kind of debugged already for you. And this is a physical prototype. You can think of it as a physical prototype. What we can talk about today and what's new is that we have a digital twin of the reference design. We call it a virtual prototype rather than a physical prototype. And this can be very, very helpful in getting you started in adding this EM field solver to your workflow as you're designing your SMP, whether it's for energy, automotive, consumer, aerospace, defense, or infrastructure applications. You can use this workflow and leverage the power device's information to get you up and running more quickly. So this is the user guide for our virtual reference design. The first one we released is for ROHM. This is the model number. It's a virtual reference design that's a digital twin of a physical reference design with this part number here, and it showcases ROHM silicon carbide power transistors, this model number here, SCT 2000 series. So the idea of the workspace that goes with the user guide is to save you a lot of work. If you open up Advanced Design System, which is our tool that includes this EM field solver that extracts the EM-based model from the PCB, when you open it up, it's a blank schematic and a blank layout, physical layout. So to create this from scratch would take quite a bit of work. Now contrast that situation with using the digital twin, the virtual prototype, which goes along with that user guide. Everything's pre-built for you. The schematics are created because the components are loaded onto the printed circuit board. We've already imported the layout from the Enterprise PCB tool. We have a library of models of all the components, and they're placed in the correct place on the printed circuit board. They have the right footprints in terms of the layout of the footprint. They have a schematic, a simulation model associated with them, and a symbol so you can instantiate them multiple times. So this is pre-built for you, and as you see, quite a complicated design, so this saves you a lot of work. So this is all very nice, but how would you use such a thing? Well, here's a workflow. You take the original design, and your goal is to clear a lane on the wire 3 level, which is yellow in this schematic, because you have to do some custom circuitry. The problem you're facing is that ROHM have a patch of metal here connecting the source of the top transistor Q30 to the drain of the bottom transistor Q130, and that's blocking you. So you need to clear this lane. You need to modify the design. The ROHM reference design isn't quite what you want. You want to make some changes. But what you want to avoid is introducing unwanted side effects when you're making the changes. You don't want to introduce voltage spikes. You don't want to introduce EMI problems. So you have to tread a little bit carefully. Now you could obviously modify the physical design and send it off to the fabrication, bring it back and plug it in. Maybe it smokes, maybe it doesn't smoke. But here, having this digital twin, this virtual prototype, you can modify and see what happens when you make changes, see if anything bad happens before you go off and fab something at great expense in time and money. So let's walk through a scenario where we do that. So just by way of illustrations, let's say the one thing we're concerned about is the shape of the turn-off waveform and the turn-on waveform at that bottom transistor, the Q130 transistor. Let's just focus on the red trace for now. I'll talk about the blue and the magenta traces in a moment, but let's just take a look at this turn-off waveform and the turn-on waveform here, and we can see it's a pretty good turn-on waveform, and there's not much undershoot here. So this is a working waveform. This is something we can live with. We want to keep this as close as possible to the original. So let's keep this red trace as kind of our template that we want to not degrade. Now the first modification we try, we just delete the patch, because it turns out there are multiple paths between these two transistors, and this metal isn't actually strictly necessary in order to make the connection. So if we just delete it, we've cleared our lane for our circuitry, and the connectivity hasn't changed. But we may have introduced some unwanted side effects. So let's go back to those waveforms and see what happens if we just arbitrarily delete this piece of metal. And let's go back and look at the traces, and look at the blue trace now. This is our first modification. The connectivity is still there as we expected, but now because the PCB trace has changed, the EM field solver, after re-extracting the new set of parasitics and running that under circuit excitation conditions, tells us that the turn-off waveform, this blue trace now, we're getting significant undershoot. And in addition, probably worse, is that the turn-on is delayed compared to the red trace. You see this gap here, this blue double-headed arrow, is indicating, when we compare the red and blue traces, that we have a delayed turn-on. Now again, ignore the pink trace for now, I'll get back to that. Focus on the red trace and the blue trace and the differences we've introduced. So we have cleared sufficient space for our circuitry, but now I've introduced two rather serious problems in the turn-on, turn-off waveforms that we need to be concerned about. Let's try something different. So the nice thing about the digital twin compared to the physical prototype is you can modify the virtual prototype very quickly, very easily and very cheaply, and get all sorts of insights in terms of waveforms and far fields. You can slice through devices and see the field inside of devices. And let's try out a different modification. We'll leave that patch off because I want to keep this lane clear. But now I'm going to add some metal on this yellow layer here, a better return path to the gate drive signal. And see if we can get the waveform back to where we were without having this obstruction here of the patch in the original design. So modification number 2 is now shown in magenta, and you can see that the undershoot is now comparable to the red trace. We've cured the bad undershoot we had in modification 1. And we've restored the speed. Now the magenta trace is almost the same speed as the red trace, and it's much, much better than the blue trace that we had in our modification 1. So we seem to have got back the performance, and we still have that nice clear lane for our circuitry that we wanted. Now in the example I showed you, in the interest of time, I just showed you one waveform. Obviously, you can look at any waveform in the design, particularly you want to focus on the nodes in the switch loop. The other thing you can look at in PE Pro is look at the far field emission and see how your modifications affect the emissions, because you want to meet the FCC mask or whatever emissions masks that you need to comply with in these high DIDT circuits. You have to worry about radiated EMI, and so he can look at the emissions. You can also look at the emission versus frequency for the worst case direction, maximum E across theta and phi, and compare that to a mask. In this case, it's CISPR 22 class A, 10 meters. And we have all the right algorithms here. We mirror what happens in a spectrum analyzer, the peak detect mode, the resolution bandwidth that's specified in the CISPR standard. So you can actually do a kind of virtual EMI chamber and get pre-compliance of EMI after making every change to make sure you don't violate things by introducing an accidental unwanted side effect for your modification where you then violate the FCC mask, which is what you don't want. So this is very powerful. So it's very brief, but let's have some conclusions and next steps. For higher speed SMPS, they can be lighter, smaller, and cheaper. But the higher speeds you need introduce new challenges such as voltage spikes and EMI failure. Suppression of these spikes in EMI by traditional solder and C workflow is costly, time-consuming, and non-deterministic. If the supply smokes or if you can't see inside the packages, you can't really fix things. So a new workflow, namely a series of virtual prototypes starting from this digital twin of the vendor's physical prototype. You can use post-layout simulation. It's cost-effective, it's fast, and it yields deeper insights because you have the visualization to suppress the spikes in the EMI. These virtual reference design, as I say, it's a digital twin of your power device vendor's physical reference design, lets you quickly and easily modify the power device reference design without introducing unwanted side effects. So please click on the link in the description below to get started, and you can download the user guide, the ADS workspace, and it contains information how to get a 30-day no-charge evaluation license of ADS to run the kit, the workspace, and try it out for yourself. I hope you'll try it, and I hope it gives you a jump start on your next project. Thank you.